Hi, my name is Nandan Singhani, and I'll be going over Lab 4 of Physics 2212, which is titled Circuits and Capacitors. The main purpose of Lab 4 was to predict the behavior of circuits containing resistors in series and parallel, as well as use multimeters to measure conventional current and potential differences, as well as examining the behavior of ohmic resistors and capacitors. The lab calculated value for the time dependence for RC circuits was 6.02 seconds. The main physics principles used in Lab 4 include Ohm's law, which states that voltage equals current times resistance, capacitance, which is equal to charge over voltage, the loop rule, which states that the sum of all potential differences around a circuit loop equals zero, as well as the node rule, which states that the sum of the currents flowing into a junction equals the sum of the currents flowing out. In order to create the initial series circuit, we will be using the Circuit Construction Kit program from Colorado PHYS project. We'll then construct a circuit with two 1.5 volt batteries, one 47 ohm resistor, one 100 ohm resistor, and two ammeters placed in the configuration shown in the image to the right. By using Ohm's law and the loop rule, we can predict the current to be 0.0204 amps, since current is equal to voltage over resistance. We can confirm this prediction by reading the ammeters in the circuit program, which read 0.02 amps, as shown in the image to the right. If the ammeters are reversed, they still read 0.02 amps. If we replace the first ammeter with a voltmeter, we can see that the voltmeter measures a voltage of 3 volts, while the ammeter reads a current of 0 amps. The reason for this is because the circuit is no longer closed. Thus, the voltmeter can measure the potential difference to be 3 volts from the battery. This is because the voltmeter does not allow current to flow through it since it has an infinite internal resistance, which also results in the ammeter's reading of 0 amps of current. In order to measure the round-trip potential difference in the circuit, we can sum up the individual potential differences of separate segments of the loop. The loop rule tells us that the total round-trip potential difference in a closed loop should be equal to 0, and if we sum up the segments shown in the chart, we can see that is true. If we were to create a graph of the potential versus the position around the loop, we would get what's shown. The differences in potential from the previous slide are graphed and still result in the potential difference of 0. If we were to use our calculated current to find the resistance of the resistors, we would use the formula resistance equals change in potential over current. This calculation results in a resistance of 47.0098, 100, 0, and 0 ohms for the 47 ohm resistor, 100 ohm resistor, wire, and ammeter respectively. When the voltmeter is used to measure the potential difference, it does not alter the ammeter reading since it has an infinite internal resistance. If we were to place a second ammeter in parallel with the 100 ohm resistor, as shown in the picture, the ammeter readings would increase to 0.06 amps. Due to the node rule, the current is split with a parallel path, resulting in less resistance. Based on the equation current equals voltage over resistance, if the resistance decreases, the current would increase. Next, we will be creating an RC circuit. The circuit will consist of a 9 volt battery, a 10 and 20 ohm resistance light bulb, and a 200 millifarad capacitor placed in the configuration shown in the image. As the capacitor is charging, the light bulb starts off bright and begins to fade. When the battery is disconnected and the capacitor is discharging, the same observation was made. During both events, the current slows down as time goes on, and when the capacitor discharges once the battery is removed, the current reverses directions. We then measured the time it took for the capacitor to both charge and discharge using both the 10 and 20 ohm resistance light bulbs. The 10 ohm bulb took 6.45 seconds to charge and 9.39 seconds to discharge, while the 20 ohm bulb took 14.07 seconds to charge and 18.72 seconds to discharge, which is explained by the current traveling slower in the 20 ohm circuit due to more resistance. In order to determine the time dependence of the capacitor in a loop with a 30 ohm light bulb, we will keep track of the voltage of the capacitor for each second in a 20-second interval. The voltage difference decreases exponentially with time as shown by the upper equation. If we then take the natural log of each side and graph the natural log of delta V over delta V naught, we will get the shown graph. The slope of this graph will give us negative 0.166, which we can set equal to negative 1 over RC. From this we can calculate the time dependence constant to be around 6.02 seconds. To conclude, the time dependence was calculated to be around 6.02 seconds. This time dependence is similar to our expected value of 6 seconds, with a percent error of only 0.3%. To reflect, if this lab was conducted in real life with an actual ammeter instead of simulated ammeters, the real-life readings would be less than the true values. This is because real ammeters have resistance, which would affect the current readings due to the current equals voltage over resistance formula. Similarly, if the lab were to be conducted in real life with a real battery and capacitor, the ideal model would predict the capacitor to charge instantly. However, the charge time for the capacitor would be slightly longer in real life than that in the simulated lab. This is because real models would have resistance within the circuit, which would slow down the current and thus cause the capacitor to take more time in order to charge. Thank you for watching.